I am Professor J.W. Hello and welcome to my lecture. P equals NP, polynomial time. What does polynomial time mean? It's basically looking at two things. P is a problem that can be solved really easily by a computer. NP is a problem that you can check for correctness very easily once solved. For example, NP is like a Sudoku puzzle. Once you have completed it, it's very fast to check and make sure you've solved it, but it takes a lot of time to solve it. The P versus NP problem / question is basically asking, are these two problems the same? Maybe trying another way. Is there an algorithm or a formula or a equation that will let a computer program quickly solve any problem that can be easily checked? Not a universal equation, but one for different problems. P versus NP excites a lot of people, like imagining the consequences of it not holding. But proving it is more of a semantic puzzle. Meta math statements about extremely general classes of objects and algorithms can be very hard to express and demonstrate. Intuitively, P should not equal NP. Intuition is a dangerous thing in math, but the consequences of P equals NP are implausible that it's hard to imagine. The real challenge is that if these things aren't the same, why the hell haven't we figured out how to show it? You know? It's a tricky statement on the limits of what we can say with our current math languages. Different field, but in my head, I get the same feel when I look at some of the wide scoped logic, theorems, halting problem, continuum, hypothesis, Gödel, incompleteness. People basically had to construct, specifically design new math languages to explore these problems because the conventional toolkit was insufficient. This can take you back to my automation theory lectures, and I don't like it. Laugh out loud. Automata. Those classes almost caused me to go stark raving mad, I'm telling you. They really did. This is an important point when pondering these long-standing math problems. The goal is not really to determine whether or not P equals NP. I don't think any serious mathematician, computation, AL scientist believes P equals NP. The real goal is to develop the language necessary to prove definitely that P does not equal NP. It's about the journey more than the destination. Many of these prominent math challenges / prizes are about finding elegant ways to prove things we already intuitively know to be true. Why would we care? Right? Why would we? Why would we even care? Because the process of discovering proof pushes used to deepen our understanding and develop new tools, and we learn along the way can reap unexpected rewards in other areas. In some ways, it's analogous to the space race. We didn't achieve anything tangible by stepping onto the moon, but the process of learning how to get there, well, and the technological advances we had to make along the way, resulted in huge benefits in other areas like materials, science, communications, tech, etc. Plus, it was cool and shit. It was cool as shit and inspired millions. It damn sure did, I'm telling you. Holy moly. Intuition is the death of basic first order logic. Set theory, basically all post 1880 mathematics. If these things aren't the same, why the hell haven't we figured out how to show it? Jesus. You know what I mean? Is that not the expected situation? If P equals NP, then there exists a problem that can be verified but solved quickly. Being able to show the difference the first time would be the solution, which we wouldn't expect to be able to find. It's more paradoxical to me. If they are the same and it hasn't been proven, Actually, speaking of Gödel, how can P equal NP if there are unprovable true statements? Wouldn't be able to verify anything with a solution and do it in polynomial time or less constitute being able to prove anything that is true. Seems to me that you can have complete or incomplete math if P equals NP. But math first has to be complete before P equals NP. I think the idea of Gödel's incompleteness theorem is that there are problems that cannot be computed at all, let alone in polynomial time. So P equals NP doesn't really have a bearing on these sorts of problems. If a non-P problem could just be brute forced anyway, not a universal equation, but one for different problems, well, all good except for this last part, right? It actually would be a universal solution if one was found because of the existence of NP-complete problems. Isn't it not being true the reason why hashes and Bitcoin mining works? Well, those things still work. Even if it's true, it's just that if P equals NP, then there is a solution out there, somewhere, that would break them. Somebody just has to find it. Merely knowing that a lock is pickable doesn't immediately unlock it. Nope. It very well may be that such an algorithm that is only faster for extremely large numbers to the point it's not practical, right? It's just that if P equals NP, then there is a solution out there somewhere that would break them. Somebody just has to find it. Let's look at it another way. Polynomial time can still have either atrocious exponents or absurd constants. We already know some pretty natural questions that can be solved in cubic time, but the constant factor is not just large, but way outside anything imaginable. Yep. That's actually directly related to the famous or infamous ultra-large numbers tree. Yep, y'all heard of that. Well, no, but kinda. What you said are examples where checking is easier than finding, but it doesn't mean finding a solution can't be done polynomial time. Some very slow algorithm for each problem, which not exist yet. It is more than the fact that there isn't a known solution is what allows those things to work. There could still be a solution that reduces the time taken to solve the polynomial time that we haven't found yet, since we haven't yet proven that there cannot be a solution. Nope. 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 Hashing and Bitcoin, by extension, indeed relies on the concept that it is impossible to reverse them. Given a hash, the only way to determine the input is to try all possible input values. They are essentially one-way functions. However, it is very much possible that the hash algorithm you designed is flawed. Oh no. Yep. This has happened where you can, for example, find two different inputs which both have the same hash value. This was demonstrated for MD5 back in 2007. Remember that? Another formerly widely used hash algorithm, SHA-1, is also known to contain significant flaws. Flaws. Yeah, you know what I mean. This means that the existence of hash algorithms does not imply that P equals NP. On the other hand, if P equals NP, literally all current hash algorithms have to be replaced, as it means the whole concept of one-way functions does not exist. It means our hashing algorithms are guaranteed to have flaws, and it is just a matter of time until they are found. Yeah. There is currently no evidence that P equals NP. So in practice, everyone is assuming that P equals NP is impossible. Maybe until we find a proof in 100 years. Maybe 1,000. Or maybe never. I tell you what, my dear friend Loretta has figured it out. She knows. I'm telling you. She knows. Can you figure it out? Let me know. Thank you. Have a nice day.